Hey, everybody. Fascinating, insightful chat today, diving into the world of NTT research with a researcher and industry insider. Hidenori, how are you?
I'm great. Great to see you, Ivan.
Well, thanks for being here. We're both in Massachusetts, enjoying a lovely summer here in Cambridge. Maybe introduce yourself, and for those who may not be familiar with NTT Research or even NTT,
Yep.
introduce your mission within the team.
Yeah. So I'm now in a really amazing setup where I'm half of myself is I'm a full-time employee at NTT Research Inc. and then which is a really visionary organization funded by NTT, which is a Nippon Telecom and Telephone, I think Japanese analog of AT&T, with a long-term vision of investing in research, fundamental research, and then thanks to the organization, I'm also a part of the Harvard University. So I'm now today physically in the Harvard University's office where I work with my collaborators in the team, where we recently jointly started this new industry academia collaboration effort titled CBS NTT Physics of Intelligence Program at Harvard University. And then I'm working on AI research and then brain science research and then merging the two to better understand both artificial and biological neural networks.
Wow, you guys have so many fascinating projects. We only have time today to talk about you and your initiative, sadly, but what's the big idea behind this groundbreaking project? And you've been at it for some time. Maybe tell us a little bit about the goals.
Yeah. So the high-level goal about this new effort, which is like putting two really big words like physics and intelligence, right? The idea behind it is that the physicist has been trying to understand the brain for a while, and then there's a really rich history physicists trying to understand how the brain works. And then the idea is to then on the other side, now AI is rising. The amount of intelligence that AI systems has, represented by ChatGPT and many other computing systems, are almost remarkable. So we are trying to say that, okay, here is artificial neural network, here is natural neural networks, which are the brain, and then we can try to find some unifying principle. So unifying universal principle is like what all physics is about, and then trying to find a mathematical principle behind them, not just about the brain, but also AI, because AI is kind of a magical system even for neuroscientists, because AI can converse, AI can draw images, like a lot of the amazing intelligence that we human have, we share it. But then everything, if you open the box of, computer, GPU, they're all the numbers. So AI models are 100% mathematically specified object where we can treat it as also a mathematical subject of study. Yeah.
Well, it's a fascinating topic. And tell us a little bit about your background, personally, professionally, and how your background in physics kind of influenced your approach to these challenges in AI. Where did that interest come from?
Yeah, so I was born and raised in Tokyo, but then I went to Kyoto University for my physics undergrad. So at the time I was working on superconductor, how, many electrons, a lot of the quantum mechanics aspect of materials. And then I came to the US to do a PhD at Harvard University in theoretical physics, applied physics, where I opened my eyes to the new entire world of biology. So I think at Harvard, it has a huge medical school. And then a lot of the physicists who used to, work on non-biological stuff conventionally were opening their eyes to biology, the complex world, because biology, again, also we get a lot of mathematical quantitative data out of, let's say, you put some electrodes in the brain and measure some activity. And then that led me then to study mathematical principles of neurocomputation in the brain. And then I went to Stanford University as a postdoctoral researcher, where we, with Professor Surya Ganguly, who is also a co-inventor of the diffusion model, the AI generation art model, what we said is that, okay, we can copy the neural computation of the brain with AI systems. So if you get some, let's say, input-output map of input is, let's say, this like visual scene that we are looking right now. And then output can be, let's say, there's a retina at the back of our eyes, and then there's a firing of neuron firing there. And then by using these input-output data, we can copy how the brain computes with AI. And then the really exciting idea there was that by looking at how this AI digital twin of the brain works, we can understand the brain through AI. And finally, then right now, I spend much of my time studying trying to understand like AI itself. So we've been doing this ambitious project of almost like a natural science of artificial intelligence over the last 5 years at NTT Research. I think we are one of the pioneers in the field, and that's what I focus on daily right now. Yeah.
Well, it's an exciting time, and you're focused on specific challenges like trustworthiness and sustainability for AI. How
Yeah.
does that intersect with the work you are doing?
Yeah. So physics is all about like understanding principles of complex systems, and then a lot of the complex systems historically has been like nature, more like natural objects. And then if you look at the history of physics, there is a story about how almost like every single industrial revolution resulted in new physics, because here's a steam engine, but then people didn't know how robust it is or how energy efficient it can be. Like, what is the limit? Then the theory physicists come in, like Carnot, who founded the field of thermodynamics, and then said, okay, this is how we can make the system more robust, trustworthy, and energy efficient. The same thing happened in the last century with semiconductors. Again, semiconductors, it's everywhere now, but then what's underlying it is the quantum mechanics, which is a really interesting but also hard topic in physics. And then physicists came in and then laid down principle about, again, like energy efficiency, robustness of these systems. And the history goes on. And I think that's where we are right now. Like, so my question was like, okay, what is a new field, emerging field that is handling complex system for engineering sake? And then that is AI. Like, AI models are making a lot of decision in society right now. But then what's scaring people is that it's a big black box, right? Even people who are creating ChatGPT at OpenAI don't exactly know how it works. And then that's where we come in as a physicist, like opening the black box of complex system and then trying to, understand how they work, which then let us control the system by finding all the knobs and how to control the knobs.
Interesting. So it's not just understanding how AI works, but leveraging that to lead to more advanced AI models.
Yeah.
So how do you think about applying some of the scientific methods from your background, your work in physics, to these? What's next with AI models?
So one of the most useful mindset and philosophy of physics that I apply to AI research is this spirit of like simplification, right? So we want to understand everything, but then there's always a trade-off. Like, the more complex the system is, the less understandable. And then what we do, just like how Newton took, like objects flying around and say it's just a single point particle, let's ignore the air friction and then return a beautiful equation of motion. We're taking AI systems, right? And then AI system, for example, show a lot of behavior. For example, a chatbot starts to say something really bad, but then people don't know like why they say such a bad things. And then there are also a post-hoc method to fix those little issues. But then again, there's a question of what is the limitation of these methods to fix it, and then is it really fixed? Because, for example, the Microsoft had some incident right after they released the Bing chatbot, and the Bing chatbot started saying something a bit scary, and then they took off the product immediately, right? And then for example, we worked on a problem related to that kind of issue, where what we said is that by applying some theory of energy landscaping physics, we have found that AI models can only hide that capability, but they can never delete them after training. So even though people tune the AI models a little bit and then think that, okay, this AI model no longer says something biased or something dangerous, what we found is that it's so easy to just make the AI model remember about what they used to do with the bad habits. And then so that also was a part of the policy suggestion for U.S. government. And so that's what.
Interesting. So, it's clear neuroscience and AI research have kind of a symbiotic relationship. But how far does that go? Is it more of an analogy, or are there real links between what's happening in both fields?
Yeah, so I think one high-level trend that I think really interesting in terms of symbiotics is that, so for example, the particular work that we done, right? The approach was to understand the brain by first copying it and then creating a digital twin, and then understand this digital twin AI. So in that sense, that's earlier work, and then now I'm doing understanding AI for its own sake. But then these two things at the end of the day are going to the same goal, right? So if we think of computer systems, there are like majorly two types of computer on the earth right now. One is a human web brain, and then more traditional computers. And then the way I view it is that all the traditional computers, if we want to make them do something, we have to write an algorithm and then code them up. So where algorithm is, if this happened, do this. There are these logical orders that we do to the machine, and then the machine just follow the logic and execute something, right? But then that's not at all how our brain work. When we see some object, maybe your face or the trees behind you, I'm not even thinking, okay, if this is a case, this is a tree. If this is a case, this is a leaf. And it's just that the neural network, which is a parallelized wet neurons, are doing computation all at the same time, and then getting to the conclusion, right? So there are these two major approach to computation, and then both our effort to understand, let's say, ChatGPT, Gemini, all these AI bots, and the effort to understand brain, at least from a theoretical perspective, both are categorized into this half. So there is a lot of convergence of neuroscientists and AI researchers trying to like hold hands in hands and then trying to understand how neural network computes.
Oh, super interesting. And you had a recent paper that looked at a new algorithm that could have potentially overcome bias in AI. Tell us about that paper, some of the conclusions, maybe, and how can we apply it in the near future?
So that's a paper that I also touched a bit earlier about. AI is not just AI is not deleting bad capability, but it's only hiding this capability. And then there is almost a physics idea behind it, where it's a theory about energy landscape. So the way we can understand how neural networks learn is that the neural network's always trying to minimize error. So when the neural network studies some new subject, right? For example, if it's a language model, given some part of the sentence, it's always trying to predict what the next word going to be. And then if the next word is correct, no error. If the predicted next word is wrong, then there is an error, right? And then the kind of physical picture is that you have this graph where the y-axis is the error. So, and then there is almost like a ball here. And then the neural network is trying to keep going down, which is like minimizing the error direction, right? But then what we have said is that if there is a biased neural network and a non-biased neural network, there's always an energy barrier in between them. So it's going from non-biased neural network to, going from biased network and debiasing it always requires the neural network to go uphill. But then this going uphill is almost like impossible after training, because that's what people call fine-tuning. You just move the parameter a little bit. You cannot really just go uphill. So I just wanted to give you some like a physical picture of, how concepts from physics can be applied to these the biased algorithm. And then what we said is that, okay, the naive given popular algorithm cannot go over this barrier. So why don't we just explicitly kick this neural network towards the barrier, explicitly? So that is a debiasing algorithm. And then there are follow-up works that we are working on towards applying it to more like real world scenario, taking this conceptual idea into reality.
That's fantastic. And you talk in your work about the mathematical theory of imagination, which I find is fascinating. And AI can generate novel ideas and designs and even art. But where does that begin, and where does trustworthiness end? With hallucinations and other things.
So
how do you think about all that?
Yeah, all the keyword that you just raised is like what I'm the most excited about right now. Like, as I said, I'm in the Harvard campus, but then the building that I'm in is actually like psychology department. So now I'm, this kind of step entering to the psychology building was one of my most unexpected, like adventurous move in terms of my, have been moving and navigating the field. Like when I was a physics PhD student, I never entered this building where my office is right now, because it was psychology department. But at the back day, when I was still a theoretical physics student, I never even thought of like entering the building, because it's even like a social science department, right? But then what's really exciting right now is that the artificial neural network are starting to, at least like partly starting to perform some behavior, like again, like talking, just chatting or just solving some mathematical problems or drawing arts, where even some psychologists who study all the remarkable things about human brain also get excited about AI because how capable they are. So that's the state of the field. And then one of the vision about this physics of intelligence program is to basically take concepts from like human psychology, and which is not entirely mathematical yet because doing experiments with human and getting numbers out is not that easy. But then we apply the concept. They still have a really beautiful concept that they developed in psychology over the years. Take them, apply them to understand AI systems. But since the AI systems are much easier to get numbers out because these are running on computers, and then we apply, theory of physics. And if I can, keep going, one of the most recent work towards this direction is as you said, the theory of imagination, where the question is, these AI models are trained on collection of, let's say, images, right? And then there is a lot of social issues because these images can be coming from a human artist, which is a really, precious artwork, but that a lot of artists has put a lot of work into. But then AI models seemingly copy some of the style of the art, for example, and generate some new image. But then the question, it's a really important copyright policy question, right? So what does it mean for an art to be new art? So that's where the theory is aiming at. And what we have been proposing is something called a concept graph. So concept graph is a kind of a mathematical object where each axis corresponds to concept. The simplest example can be just this is a color, axis of color and size and shape. So what we say is that there are these underlying concepts behind these images. And then we put all the pictures on the graph, and then we can define distance, which is going to quantify how novel the generated image is in light of what the neural network has already seen. And
amazing.
Yeah.
Well, it sounds fascinating. Looking at other, initiatives in the world of AI, you're getting into practical use cases with brain AI interfaces today. We've seen amazing progress there. Do you see that as a reality? If so, how far in the future do you think we have to go to see the scale?
So in the long term, I believe so. And then actually, I am really enjoying one of the amazing collaborators that I'm fortunate to work with is a group of Professor Mark Schnitzer at Stanford, and then there is amazing student Farti Dink, where they have been leading they are the world expert on building a neuroscience experimental system where they can record from tens of thousands of neurons from the brain, neuroactivity recording. And then what we have been trying is that I'm more of a software person, like I develop algorithm, etc. So the vision is to train digital twin artificial neural network on the side of the live recorded brain. And then another amazing technique is they don't just record it. They can apply light to individual neurons to turn them on and off. So what that opens up is that, we can use this digital twin to compute how to apply feedback to control the brain state in the way we want, right? So that's amazing. A kind of, so we're not, and these are still with mice and animals, but then I don't know, it was fascinating, but also almost like it's like too powerful to, and then it was, I'm also half scared about the possibility of, like we can just shine light and then turn neurons on and off, but it's technology to be explored, and that we are, working on that.
Incredible applications for good there, I think, as well. And, looking at your team, your larger team, what are some of the other goals that you're focused on, not just this year, but in the next few years?
So in terms of my team, there are two levels. I'm leading this AI research team within NTT Research, but then I'm also part of an even bigger organization where a lot of the hardware folks exist. So let me just talk about my group first, and then maybe more overall. So one of the focus area that we are thinking right now is actually the issue of like AI trustworthiness, and then beyond, the narrative is actually recently going towards safety, given how fast the progress in the field of AI is. And I think that is like I sit in academia, and then in academia, we think about things in a time scale decades. It's not just about shipping some product in half a year.
Mm.
So even though, like, admittedly, there are just many technical challenges right now to, let's say, take this ChatGPT and then turn it into like human, AI humanoid or something, that will still take some time, or that there are at least there are a lot of technical issues that we can see. But then given the pace of the progress, I don't think it's too early to start thinking about, all the kind of like a safety related issues, like more real issues about AI system in the time scale of, let's say, like a decade or, a couple of decades from now. And then I'm really hoping to basically work together with people to build this new field where a lot of scientists who used to study or who are studying natural complex system, I think we should all pay more attention to artificial system, because the complexity of artificial system that we can build are partly reaching some complexity that's going to match the complexity of, let nature say, or some like biological organisms, right? So that efforts, that kind of shifting of attention to AI is like one aspect. And then also on the other side, there are a lot of policy people, people working in the government trying to ensure AI, making AI safe. And then I think building this new field, which is like rapidly becoming important, that doesn't exist really yet, together with my collaborators. So that's like one of my broad vision of, natural science of artificial intelligence for building safe AI systems. Yeah, so that's.
Well, what wonderful work. Wish you all the success there. I guess lastly, I would just ask you any advice to younger professionals, maybe undergrads even, or other stages who are interested in this emerging field of physics and AI and and both research and industry. What would you advise them to do now to kind of get in the game?
Yeah, so I'm really biased, but then I would really encourage people to just be adventurous, in the sense that even, and that's been one of my keyword, in the sense that, what I work on is, as you can see, it's not that traditional. I mean, there are amazing physicists working on more traditional subject in physics, and then taking every step, at least when I was younger, every step felt more scary. But then I think there's one quote that I really love from Steven Weinberg, who is one of the founder of particle physics. What he said as a advice to young people is go for the messes. That's where the action is. So even the particle physics, which has like one of the most beautiful theory of physics, when he has founded the theory, built the theory together with people, what he said was that the entire field was just a messy thing, because a particle accelerator just like built, and then people thought that there are only little number of elementary particles, but then the accelerator found like so many particles, and then people felt like it's the end of physics because it's just too messy. There is no clean principle. But then actually, job for physicists to just clean up the mess and then turn it into something beautiful and clean, simple. So don't be scared too much about the messiness of some of the emerging field. Just dive in and then clean the mess, which will then hopefully become a new build subject. Yeah, that we can pass it to the next.
That's fantastic. Yeah, AI is an amazing lens through which we can explore the universe. And congratulations on all the work with you and the team. You're quite a unique organization. I don't know anyone like you guys at NTT Research, so keep up the great work.
Thank you.
Thanks so much. And thanks everyone for listening and watching, and follow NTT Research on all social channels. They put out some amazing research, obviously, and content, and it's really worth giving them a look. Thanks so much.
Thank you.
Take care.